So today we have the Parker direct drive precision direct drive rotary servo motor, and it has a very fast move and settle capability. It's tends to be a high voltage winding, but the speeds 500 RPM max. The volts per kRPM are not specified, but the Newton meters per amp RMS are, and that works out to about 200 volts per 1000 RPM, so typically a higher 120, 240 volts AC, but today we're going to use 48 volts, and we're not going to go too fast, maybe the rated speed 200 RPM. We see specification data for peak continuous torque inertia. There's no inductance and resistance in the specification sheet, so we'll use our ohms meter to measure it. Looking at the drive, this motor has a BiSS encoder. It's a 20-bit BiSS encoder, and there's some special configuration for it, and we'll take a look at that. But basic wiring is clock. Clock comes out of the drive, goes to the motor, and then data comes back. If we used an oscilloscope and took some measurements, we might see the clock going out to the encoder, and then the encoder reads the absolute position once per rev. This one's not a multi-turn, and then it will return with the data during the clock back. We could try to monitor it with CME scope, but not so good, so my recommendation is to use an oscilloscope. And of course, when measuring winding resistance, you can just measure between pairs of wires. That's the earth, and then you got your UVW here. Just measure between, make sure the drive's disabled, but just between these two pins, or you could disconnect it from the drive. I measured 10 ohms, so if the motor is doing 1 amp at 10 ohms, that's 10 volts. So you got some IR drop with such large resistance. I expect large inductance. I don't have an inductometer today, but we did some tuning, and we could see that the inductance was rather large. And let's see, we're connected here with CME. Go through the basic setup required for the BiSS. So BiSS on the motor. This case is no load, but it's a direct drive motor, so we are measuring the load. 20 bits. There's no multi-turn. There's no alignment bits, although it may say something about alignment bits. It's not. Even if it is a 21-bit encoder, we did not use an alignment bit. What we did is we set active low errors, and the format was the protocol was position, alignment bits, if any, and then status. And we ran it at 2.5 megahertz. And of course, at the servo loop rate for the velocity and position mode, don't use current loop rate unless you're in a current mode only. And I believe the 2.5 megahertz is part of the spec. Do not use the encoder filter to ignore CRC faults, fixture cabling, grounding, shielding. Yeah, just another back to the shielding. You can see there's an outer braid, and if there's an inner foil with individually twisted pairs, that goes to signal ground. But usually it's just one drain wire for the outer braid, and that goes to the drive frame ground, which is the drive metal is connected to earth, so the shield finds a good path to earth. I would not connect the shield to the motor case. On the bench here, my motor case is not bolted to the frame, so all the noise is going to go down my feedback. I didn't measure it in this case, so I assume they did not wire the feedback shield to the case of the motor because everything's working. Looking at the motor spec, again, the Newton meters per amp RMS is given in amps RMS, and the volts per radian per second. If I go to Newton meters per amp peak, I get 1.9516 Newton meters per amp peak, and that's the same for volts per radians per second. So I just set them the same. 1 Newton meter per amp equals 1 volt per radian per second, typically for most motors, unless it's a delta winding. I think this is a Y winding. Volts per K RPM, 200 volts. So that's why, you know, at 100 volts, you're only going to go, plus you got some IR drop. So let's take a quick peek at the current here. These are calculated from the good data. We got your 1.5 amps and your 4 amps. So 4 amps times 10 ohms is 40 volts. At 48 volts, you're not going to do peak current, obviously, and unless you go really slow, right? So you need lots of volts for back EMF and lots of volts for IR drop. And oh, by the way, the inductance turned out to be about 30 millihenries, and I kind of backed into that by tuning the current loop for, I forget what the bandwidth was, but let's take a look. So I kind of backed my way into values for CP and CI based on the calculation. 500 hertz of current loop bandwidth is sufficient for a motor not going very fast with 10 poles, or sorry, 20, let's double check that. 20 poles, 10 electrical cycles going, you know, 60 RPM, 1 rev a second. That's going to be 10 hertz, and then going the full 200 RPM, less than 500 hertz for sure, more like 80 hertz. So the bandwidth for that is fine. I moved this limit from 250 to 500, but we'll never hit it with the 48 volts anyways. I tuned the velocity loop, and I did move the filter pole out to 500 hertz because I wanted a little bit faster move and settle. And these gains that were adjusted are for no load condition. Although you probably don't have to change your gains for VP and VI, no load or full load. Sometimes if you have a big mass, yeah, maybe you can, you know, bring the pole in and then crank up the gain a little bit. But this is guaranteed not to buzz with no load and full load, right? So don't set the gains too high if you're going to have a no load condition. This is a no load condition, so I cranked up my PP, so I got a very fast move and settle. If there's a big mass, maybe you want to cut this down. It's kind of a inertia, motor inertia to load inertia, 10 to 1 versus 100 to 1, you know, maybe 20 for 100 to 1 and 200 for 10 to 1. But I'm going to make a simple trapezoidal move here. This will be 1 rev at the motor, and we'll take a look. So 1 rev of the motor. Trajectory limits were set to 200 for XL and decel, 42 revs per second. I used about no load 0.3 amps. Wow, and I got a whole like amp and a half. So while I'm at speed, current comes down, so not a heavy preload, nice and stiff. You can see the voltage limit warning. I got 48 volts and I'm trying to go 200 RPM. So that's on the edge of not working with 48 volts. But if you cut your speed down, and again, watch your IR drop, depending on how much current you consume, you could get some voltage limiting while you're XL and decel. But at this speed, there's no voltage limit warning. Although I do like the 200 RPM because it fits on the screen here. And the move and settling, I cranked up the integral. I get within 5 counts. You know, a slight little bounce here. It was a little more bouncy with the 200 hertz 2-pole, but I moved it out to 500 hertz, so I get a snappy response on it. We could move it out further, but don't forget, you can't have more bandwidth than your current loop bandwidth, so 500 hertz equals the current loop bandwidth 500 hertz. You need more voltage to push that current loop bandwidth further out, crank up the gains, maybe a little bit, 10%, 20%. Try to get a kilohertz if you can with a higher voltage, and then you could push the velocity loop bandwidth out to 800 hertz, maybe a kilohertz, depending on how much current loop bandwidth you got. And it might be a little snappier, but this looks well damped. I'm pretty happy with it. I did crank up some integral here a little bit more than normal to try to reduce the steady state error. But other than that, it's tunes up really well. No load again. I doubled my PP. And one last thing on power up or reset. We can do absolute immediate home once per rev. And again, like I've been spinning this thing, so to get back to absolute zero, it's going to take a few revs. But there it is. So this is my zero position once per rev based on a single turn absolute encoder. So I'm at the zero position. I put some tags on it. That's my zero position. But you could always like just slap your mechanical system together willy-nilly, and you can get like a once per rev home position. And you would do that by using activate immediate home. Also, I'm not using it today, but you could use a position wrap. It will always take the shortest distance to the absolute position with the wrap turned on, and that's the counts per rev 2 to the 20 or 1 million. Yeah, 1,048,576 counts per rev. You could set that, and it would do the wrap. I think that's pretty good for what I did here for setup and tuning, and left it in a can mode, and BP2. I just copied the A axes to the B axes, assuming that this BP2 would have two motors that are exactly the same. All right, yeah, big thanks to Parker for providing the test file. I guess the guys at Parker had used the Copley and they saved the file, so they made the configuration pretty easy for me. So big thanks to the Parker guys, and thanks for watching.